How do you control something longer than many cities' main streets? And what economic pressure justifies pushing rail engineering to that extreme? In June 2001, deep in Western Australia's Pilbara region, BHP's Mount Newman Railway tested a 7.3-kilometer iron ore train, an industrial leviathan spanning the desert. Subscribe and join this investigation where we reveal not spectacle, but the hidden constraints behind moving nearly 40% of the world's seaborne iron ore, and how every delay can ripple through global steel supply. When port space, mine output, and rail schedules collide, the only lever left is train length, setting the stage for a battle between physics and economic survival. A port planner in the Pilbara doesn't see trains as moving steel. They see time, dollars, and risk running on rails. Every hour, a ship waits at Port Hedland's berth. Costs stack up. When the market for steel tightens, even a 1% shift in Pilbara's iron ore exports can nudge the global spot price by $5 a ton. With BHP, Rio Tinto, and FMG controlling nearly 40% of world seaborne iron ore, the stakes for every shipment grow larger than any single train. In the early 2000s, the region's mines were pushing toward 80 million tons a year, but the system had limits. Mine output capped by truck fleets and crushers, port loaders working at full tilt, and a single-track railway with only so many slots each hour. Adding more trains was not an option. The signaling network could only handle about 6 train paths per hour. If they added more, the whole timetable would grind to a halt. The math was simple and brutal. Running 2 standard-length trains instead of one giant would mean more crew, more fuel, and more time lost shuffling for position. But stretching a single train to 7.3 kilometers, enough to carry over 82,000 tons of ore at once, cut locomotive hour costs by nearly 30%. That is not just an accounting trick. It freed up port loaders for bigger ships, reduced the number of train-to-ship transfers, and squeezed more value from every slot on the line. The decision to run a train longer than a city's main street was not about breaking records. It was a last lever, pulled when every other part of the system hit its ceiling. The planner's calculus showed that only by scaling up to the edge of what the rails could bear could Pilbara keep its grip on the world market and avoid leaving millions in revenue waiting at anchor. That relentless pressure set the stage for a new kind of engineering, one where physics, not just ambition, would decide what was possible. On a train stretching more than 7 kilometers, brute force alone is never enough. The real challenge is control, taming the physical stresses that threaten to tear a formation apart before it ever reaches the port. Heavy haul engineers speak in numbers that rarely make headlines: drawbar forces, coupler fatigue, brake propagation time. These are the invisible boundaries that define what is possible on rails. Start with the couplers, the steel jaws linking each ore car. On the Mount Newman record run, every connection faced tension and compression as the train accelerated, climbed, or braked. Engineers measured longitudinal forces along the line, keeping each drawbar below 12 kilonewtons during acceleration. That is the difference between a safe journey and a catastrophic break, especially when a single parted coupler can sideline 100,000 tons of cargo. A brake specialist explains, it is not just about how much weight you can pull. It is about managing the surges that ripple through the train with every throttle or brake command. Harmonic waves can amplify forces far beyond what the steel was designed to take. Distributed power, locomotives placed at the front, middle, and rear dampens those surges, cutting peak loads by nearly half. Braking is another world of constraint. Conventional air brakes send a pressure wave down the train's length, but over 7 kilometers that signal can lag for nearly 2 minutes. Electronically controlled pneumatic brakes, known as ECP, change the equation. With ECP, brake commands reach every car in under 250 milliseconds. The result is stopping distances shrink by more than 1 kilometer, and the risk of jackknifing or run-in is dramatically reduced. On the Mount Newman run, ECP kept run in forces below 0.8 G, well within the fatigue limits of the Janney-type couplers. Braking mattered as much as raw mass. Safety did not stop at hardware. The train occupied as many as 7 signaling blocks at once, a rare exemption granted only after regulators reviewed risk models showing the probability of a major incident remained under 5 per million train kilometers. Every control system, from staggered throttle commands to emergency brake protocols, was designed to keep the physics on a tight leash. In the end, it was not horsepower that set the record. It was the ability to predict, measure, and contain the forces at play. The lessons learned here would shape not just Pilbra's future, but the global playbook for running trains at the edge of industrial scale. Safety and foresight proved to be the decisive factors. Across the world, 6 other rail giants have each confronted a different limit, and in doing so, redrawn the boundaries of industrial scale. In South Africa, the Sishen to Saldanha iron ore line faces the brute reality of weight. When an overloaded ore train derailed near Kimberley in 2015, investigators traced the cause to axle loads that reached 42 tons, far above the original track design. The response was to upgrade rails and reinforce couplers, or risk catastrophic failures as mass outpaces infrastructure. Mauritania's iron ore corridor stretches nearly 700 kilometers through the Sahara. Here, the constraint is not just distance, but relentless exposure, sandstorms, heat, and minimal maintenance. In 2018, a sandstorm triggered brake fade on a train 600 kilometers long, sapping pressure from the brake lines and forcing an emergency stop at a remote siding. Operators now fit sand screens and redundant pneumatic lines, knowing that reliability means survival in the desert. China's Daqing Coal Railway offers a different challenge: frequency. With over 180 trains moving daily, the system's bottleneck is not length, but how many trains the network can safely handle at once. In 2020, a double-stack coal train overloaded a bridge, collapsing the structure and halting traffic for days. The lesson is clear: throughput depends as much on scheduling and infrastructure balance as on raw tonnage. Union Pacific's 2010 experiment in the United States put length to the test on a mixed traffic corridor. A 3.4-mile double-stack container train derailed near Los Angeles after failing to clear a curve with adequate margin. The incident highlighted how shared freight and passenger networks impose strict limits on length, with signaling and siding geometry as the final arbiters. India's Super Vasuki, assembled in 2022, links together multiple coal rakes into a 4-kilometer formation. When a coupler failed mid-run, the blockage lasted 2 hours, stalling an entire corridor. Indian Railways now invests in real-time coupler health monitoring, betting that predictive maintenance can keep these mega formations moving. Japan's Tokaido Shinkansen N700 series redefined scale not by length, but by velocity and reliability. In 2019, a brake system software glitch delayed emergency braking on a run at 300 kilometers per hour. The fix was continuous diagnostics and automatic fallback modes, because at these speeds, every second counts. Each case shows a different trade-off. Push one boundary, and another becomes the new limit. The physics of scale never rest. Regulatory scrutiny always circles back to a single question: is the risk of extreme scale justified by the benefits? The answer across every case is conditional. Ultra-long trains are not a default tool. They are a calibrated response to bottlenecks that cannot be solved by more conventional means. In the Pilbara, the verdict was shaped by a system where port congestion, limited rail slots, and global market volatility demanded a solution that could move more with less. But each lever pulled to stretch the system, such as longer consists, distributed power, and advanced braking, concentrates risk into fewer, larger movements. The reward is efficiency. Fewer crews, lower fuel per ton, and less congestion in narrow corridors. The price is a steeper cliff if anything fails. Regulators weigh these trade-offs in terms of controllability, not just headline numbers. The lesson from the Mount Newman trial and its global peers is that physical limits like coupler fatigue, brake signal lag, and track geometry are not theoretical. They become operational boundaries, enforced by the laws of physics and the cost of failure. In South Africa, axle loads were pushed only after reinforcing track and couplers. In Mauritania, reliability takes precedence over speed because a breakdown in the desert is an existential risk. China's Dakin line shows that frequency, not length, can be the dominant constraint, and that infrastructure balance is as important as raw throughput. The Union Pacific experiment in the United States underlined that mixed traffic networks impose limits that cannot be overcome by power alone. India's Super Vasuki and Japan's Shinkansen each reveal that coupling complexity and velocity introduce new forms of risk, demanding continuous diagnostics and predictive maintenance. From a regulatory perspective, the verdict is clear. Extreme length is a specialized instrument reserved for corridors where the economic upside outweighs the operational hazard. Every exemption, every override, is granted only after models show that risk remains at or below accepted thresholds. The lesson for policymakers is that there is no one-size-fits-all answer. The ceiling for train length is always set by the weakest link, whether that is steel, software, or the human at the controls. As automation and smarter control systems evolve, these boundaries will shift, but the regulator's core principle endures. Scale is negotiable, safety is not. Today, iron ore from Pilbara still feeds over 30% of global steel. As supply chains tighten and climate targets loom, the future of rail hinges less on brute scale than on precision, automation, and control. The real frontier is invisible, and every constraint we master shapes tomorrow's world. Stay curious. Subscribe for more investigations.